All right, everybody. Last material, if we get through enough today. Last new material. Well, for this class, I don't think we'll get through it all today, but the stuff that we'll have left for next Thursday is the fun stuff, like how do you build a fusion reactor? How do you build an atomic bomb? Things like that. Yeah, we don't have any labs on it, unfortunately, but all right. So here's the basis of what we covered the other day on whatever day it was, Tuesday. This is a really good recap of the types of nuclear decay, of radioactive decay. Alpha particles, beta particles, you have gamma, then you have positron emission and electron capture. And remember, the gamma radiation gets named as a type of radiation or of radioactivity, but it's not really its own thing. It's basically just a way that it gives off energy, right? So the main things to look for on questions like the worksheet from yesterday is just, can I put it into one of these categories? And oftentimes, if it's a more general reaction, like uranium-235 plus a neutron goes through a fission reaction, if it just says goes through a fission reaction, I've got to give you what the products are, basically. So turns out uranium-235 going through a fission reaction is a pretty important reaction because that's the one that that they use to make atomic bombs. I'm going to save that for when we get to the slides on atomic bombs because it's got some other concepts in there. But basically, I have to tell you what it is if it's not one of these types of decay, right? So as long as you know these, that's all you're going to know for. And I think that's one of the 10 parts on the final exam. So 10% of your final exam is this slide. Right? So that might not sound like a good thing right now, but trust me, these are pretty straightforward when you get the hang of them. Right? So let's practice. Let's do. There are some isotopes like potassium-40 they can go through two different types. They have a different probability of going through one of two different types of decay. You can either emit a beta particle or go through electron capture. Let's write those reactions out, including the products. I'll give you a few minutes. All right, how do I know how to fill that one out? First off, which one is this? Electron capture or beta emission? Beta emission. We're emitting something. We're losing something. It's not electron capture because we're giving something off. So then as long as you know what a beta particle is, you say, okay, well, here's my starting material. I know it's giving off a beta particle, which has a mass number of 0 and a charge of -1. Then we just fill in the other side. The mass didn't change. In order to make the mass number balanced between both sides, it's still got to add up to 40. So 40 here, 0 plus 40 there. As far as the number of protons, we need this bottom number to add up the same amount. Got 19 here and a -1 there. So 20 plus a -1 gives us 19. Everything's still balanced. We're just balancing it in terms of protons and neutrons instead of just looking at carbon atoms, for instance. One thing I will say about the worksheet that had, I think the worksheet had the protons on the right-hand side.
It's weird.
Yeah, I do think that that's weird as well. It gets confusing because then it looks like it's a subscript, like you're saying how many atoms there are, right? If I wrote that, is that hydrogen gas or is that, or sorry, that's a typo anyway. Or is that a diatomic molecule of helium or is that helium-2 as an isotope? Hard to say. So we put the protons on the bottom left instead of the bottom right to avoid that. Subscripts on the bottom right are always how many of an atom you have. On the bottom left are what's the atomic number or how many protons do you have?
Yeah, you guys, when I grabbed that worksheet, it was like, it was a decent one except for that, and I didn't want to confuse you guys when we were talking about that. So definitely not how you would think.
So this way is going to be the way I was consistent with this. When you're studying for this, and when you're checking your answers, things like that, this is the slide that I would go back to, this table, or if you can find something similar that's, but if you look at the way everything's written, for when we're talking about nuclear reactions, everything's written on the left-hand side of the atomic symbol because we're talking about mass number and we're talking about protons. All right, so if it goes through an electron capture instead, what changes? Still starting with the same material. If it's capture, am I making another product or do I have another reactant? Yeah, another reactant. What is the other reactant then? It's electron capture, right? So you can write it as an electron, but to be consistent, you might as well write it as a beta particle since they're the same thing. Mass number still not changing, right? Positron emission, beta particle emission, electron capture, all of those have a massive number of 0. So for all of those, your mass is not changing. It's just how many protons you have is changing. I'm not going to fill in what the element is yet because first, before we do that, we need to know how many protons we have, right? So do protons first, 19 plus -1, which means whatever's on this side has to add up to 18. So argon. As long as you know that summary slide, that table of the different types, balancing these shouldn't be too tricky, right? It's just getting familiar with the vocab and reminding yourself what it means. Do you have any questions about the worksheet from yesterday or about what we've covered so far for nuclear reactions? Well, let's press onward then. All right, so potassium-40 can go through 2 different types of radioactive decay. Most of the really big ones, like uranium, go through alpha decay. How do we know, is there a way that we can predict what type of radioactive decay it's going to go through? Well, if we knew more about strong and weak nuclear force, if this was a nuclear physics class, we'd dive down into the numbers and actually do some calculations because you can predict, it turns out, what you're trying to do with any of these radioactive reactions is you're trying to get closer to the right ratio of protons to neutrons in a nucleus. If you get the right ratio of neutrons to protons, you get a stable nucleus that doesn't go through any of these, basically. Like carbon-12, doesn't go through any of these processes. Carbon-12 has a very stable ratio of protons to neutrons, so it just is stable on its own. If you gave it till the end of the universe, unless it gets sucked into a star or something like that, it's going to stay as carbon-12. Right? So basically, we're going to see these reactions when we get away from what they call the valley of stability. Nuclear physicists get really colorful with the way they name things because they're a poetic bunch, right? I've become death, destroyer of worlds. They all had a pretty high view of their self-importance, which arguably was justified. They did, collaterally destroy 2 cities, testing some of this technology out. The valley of stability is basically anytime you get that right ratio, and it kind of changes a little bit. It's not a straight line. These green dots are basically all the stable isotopes that you can have. And so if you look at the axes here, number of protons, so every column basically, since we're dealing with discrete numbers, every column is a different element. Right? And so you'll notice that a lot of different columns have multiple stable isotopes. At least relatively stable. Stability is relative. We'll find out in a minute. But what you get is anytime you get too far away from that ratio of protons to neutrons, we're going to see we wind up in this white area, which is not stable. And basically, it'll go through a radioactive decay until it gets to one of these stable isotopes. It's kind of like, I don't know if you go to the top of a gun barrel at Heavenly and you roll a bowling ball from the top. It's going to go all the way to the bottom unless it happens to hit a stable point along the way, right? These green dots are the stable points along the way. It'll keep going through radioactive decay. It'll keep moving downhill in energy until it hits a stable resting spot. Turns out that's the way that energy works in our universe for everything. Every reaction, every molecule will keep going through reactions until it gets to something stable like that. And even that stability is kind of arbitrary. If we had too many neutrons, if we were on the uphill side of the valley stability, if we have too many neutrons, what kind of decay would make sense? We have too many neutrons. We're trying to turn some of those neutrons into protons then, right? That's going to affect our ratio. And you can go through alpha decay, but that's basically you're losing the same number of protons and neutrons, so your ratio doesn't really change that much. So it can go through think about it in terms of it's either going to give off a beta particle. If you give off a beta particle that took a neutron and turned it into a proton, right? We have more protons now than we did when we started. If we start with too many neutrons, beta particle decay is going to be the most common type of decay, right? Because we have, right now, our ratio of neutrons to protons is 21 to 19. If that ratio is too high, take one of those 40 and turn it into a proton. Now we're looking at 1 to 1. So we got closer to that ideal ratio. We found a more stable isotope by turning a neutron into a proton and losing a beta particle along the way. So with that in mind, what about if you have too many protons? If you have too many protons, you've got the opposite problem, right? If you've got the opposite problem, we should probably use the opposite sort of decay. It'll either go through electron capture or it'll go through a positron emission, which has the same net result. All right, because remember, a positron is a beta particle with a +1 there instead of a -1. That's all sort of backgrounds interesting because I'm not really going to ask you to predict that on the final. I want you to understand kind of what the value of stability is. That's fair game for like a vocab question. And I would expect something to answer like it's any of the isotopes that have a stable ratio of protons to neutrons. Don't need to know what that ratio is. We can look at the periodic table and kind of guess it if we look at where all these stable isotopes are. But that's kind of the level that I want you to think about this for right now. What happens right here when you get to, it's about 82? What happens when you go past 82? Yes, if that's 80, that's 81, 82, 83, 84. There's one stable isotope for 84. What is 84? I think I counted wrong. That's 83. What's 83? Bismuth. What happens when you go past bismuth? What do you notice about all of these atomic mass numbers when you go past bismuth? They're all in parentheses, right? What do parentheses mean? It created something unstable. Usually that means that it's either unstable or just that it has no stable isotopes. They can be naturally occurring in some cases. It depends a little bit on the periodic table. But if you look down here, like, I think these ones still have actual numbers. Like I said, depends on the periodic table. Some periodic tables will have everything past bismuth will be in parentheses, even the ones that are naturally occurring. Because everything past bismuth, there are no green dots past bismuth. Everything past bismuth is radioactive. Every isotope of it will break apart some way because you just get to too large of a nucleus to be held together and it start breaking apart. Think about building a nucleus like building something out of Lego. If you build stuff out of Lego, it seems really stable at first. If you just took, I don't know, 4x2s and started building up to the ceiling with it. Seems pretty stable at first until you get, 5 feet high. And then if you move it the wrong way, it falls apart, right? Once you get to a certain height, there is no stable way to do that because your whole tower is going to come apart, basically. That's what happens with the nuclei. And like I said, most of those ones that are past bismuth are just going to go through alpha decay, or they'll go through some combination. Do I have they'll go through what's called a decay chain. So decay chain is basically, this is the same graph where you have number of neutrons here and number of protons is on the X. If you start with one radioactive isotope, this decay chain or decay series will basically go through a bunch of steps until it gets to something stable. This is our bowling ball running down the hill. So uranium-238 starts by giving off an alpha particle and becomes thorium-234. We saw that one on Tuesday. But then sometimes it'll actually give off 2 beta particles and go back to being uranium. But now it's uranium-234. And uranium-234 gives off alpha particle, alpha particle, alpha particle, alpha particle until it hits polonium. When it gets to polonium, now it's got a mass of 218. And then it has a couple options. And all of this, maybe a bowling ball running downhill is not the best analogy. It's like a pachinko machine. Put a marble at the top, it bounces its way down to the bottom. Everybody still watches. I guess with streaming, you probably don't have the experience of having a sick day when you're a kid in elementary school and the only thing on is The Price is Right. My generation, when you stayed home, you had 5 channels to choose from, and The Price is Right or soap operas were your choices when you were a middle schooler stuck at home. I watched a lot of The Price is Right. So Plinko is the game that they play on The Price is Right. You put a little thing at the top and it bounces down. If you've never seen The Price is Right, I think you can get it. You can stream it for free on all sorts of different networks. Worth watching. Nah, maybe not. It's a cultural experience. Where is this going to stop? Not specifically, but what's gonna cause it to stop? It's gonna keep falling downhill until what happens? Probably not no more neutrons. That'd be like getting all the way down to hydrogen. Little bit of neutrons. Basically, it's gonna fall downhill until it hits one of these green dots. These green dots are stable enough that once it happens to land on one of those, not happens to, it's going through this process because it's going to end at one of these. Where am I going? So this is more on the theoretical side. This is another view of the same thing, except they use height to represent stability instead of the valley of stability. They call it the island of stability. Basically, if you get into the theoretical physics and you start looking at strong and weak nuclear force and all of these different variables going on, the physicists have predicted that there are some stable isotopes of some of these super heavy elements. Right? So when people wind up, inevitably asking things like, well, why bother going past the end of the seventh row? We just keep making things that are also unstable. We're just getting further and further into the sea of instability, except that our predictions say that there should be a couple of stable isotopes out there that are really, really heavy elements. This one, if you look at the proton, I think that this is an old chart. It's shifted. I believe now the current understanding is that when we get to about 122 to 125 for the atomic number. So that's going to be, if this is 118, we're talking about some stuff that's right in here in row 8. If we can build a particle accelerator large enough, strong enough to be able to make some of those, we should be able to make some elements that have literally never been seen in our universe, barring the existence of aliens that are better at technology than us. We don't know. Maybe they might be really good superconductors. They might be really, really dense and really helpful for building good alloys. So we don't know. We can predict some of the properties, but we don't know. But they should last long enough. They should be able to last in the years to decades to centuries range, compared to most of these isotopes that we can make artificially have half-lives that are basically in the minutes. It's hard to build a spaceship out of something that breaks down on the order of minutes and microseconds and things like that. But it should theoretically be possible. So that's one of the things that keeps science going. Like, well, what if we did that? Let's try it. What'll happen? World explodes. How do we know that those elements cannot be found anywhere else in the universe? We have a pretty good idea, though. We don't know for sure. There could be other intelligent life in our universe that is better at technology and has figured out how to do this. But we do know that it takes more energy than you can find in a supernova. So there's not really any naturally occurring system in our universe that we're aware of that could make something with an atomic number in the 120s, which is kind of interesting. That's kind of cool. That would be really unique. Then it's truly a synthetic element. The rest of these synthetic elements, we call them synthetic elements because they don't show up in our solar system naturally, but they did at one point. Our solar system is the result of a previous supernova. So there was a star that before our sun that went through a supernova and produced most of the things on the periodic table in some amounts. But all the ones that decayed really quickly were gone before we knew to look for them. Technetium is a good example. Technetium is is the earliest element that has no stable isotopes. Which, now that I think about it, there should be a column in here with no green dots in 43. I don't quite, it's probably in between those two. There's a gap in between right there. Anyway, the supernova that produced our solar system did make technetium. We call it a synthetic element because we don't see it anymore. But it has a half-life in the 50,000 year range. I want to say it's like 43,000 years. The most stable isotope of it does. So that means that every 50,000 years, you have half as much technetium as you started with, which sounds like a really long time, except that the first, I don't know, 2 billion years of our solar system was just rocks bouncing into each other and not really anything looking around to see, hey, is there technetium over here? There probably was. Actually, there almost certainly was, but it was just gone before we knew to look for it. All right, so what is this energy that's driving all this? I keep saying it's the right ratio of protons to neutrons. We talked about nuclear binding energy the other day, right? We got to do a calculation with nuclear binding energy. We used fluorine as an example, right? Nuclear binding energy is pretty easy to calculate, like we saw on Tuesday, except we're almost never actually going to be looking at the entire, separating every subatomic particle from each other in the nucleus. We're never actually going to be taking an entire fluorine apart all the way down to its bare pieces. Most of these nuclear reactions still have nuclei on the other side. They still have larger particles. So for the most part, when we're talking about these nuclear binding energy reactions, we're going to be comparing products minus reactants. And so, I guess, let me add one more flavor diagram here. This is kind of fun to think about a little bit. Basically, there's a sweet spot. It's not just the ratio of protons and neutrons, it's also total number of protons and neutrons. This yellow bar right here is where you have the highest possible nuclear binding energy. In other words, those are the nuclei that are most stable. There are stable nuclei that will stick together, but they could be more stable if you forced them into more fusion reactions or through more fission reactions. In this range right here, from this is the mass number that goes, it's mostly iron. Iron, it turns out, is the most stable. Hey, good.
Do you have big tables also? Any scales? I use the one from the
So basically what this is telling us is that on a long enough timeline, every nucleus in the universe will eventually settle into the most stable possible nucleus, which is iron. Everything eventually ends up iron if you go through enough supernovas, because once you make iron, it can't get more stable than that. And if you get too many iron atoms at the heart of the sun, it actually doesn't go through a supernova. It goes through other processes. The star will still die and explode and expand, but when it recontracts and starts going through fusion reactions again, it won't burn as hot as it did the first time because you've got too much iron and the iron's already too stable. Which is kind of interesting to think about. This is one of the ways that even if we didn't have ideas like the big crunch, the opposite of the Big Bang is the big crunch, happens when everything contracts at the end of the universe. Eventually, we'll stop making new stars. I say we, like we have a choice in this. New stars will stop forming because everything will already be so stable. Everything in the universe started as hydrogen and helium with maybe a little bit of lithium and started forming stars. And the stars were just fusion reactors where you kept making more and more heavier atoms, and then they explode and you get lots of atoms, and then they come back together and you make new stars. That process can only go through, I want to say that the number I saw most recently was like 10 iterations. As you get more stars, or as the stars go through more and more generations, they will burn less for shorter and not as hot. And you won't make as many of these larger atoms anymore, which is kind of interesting to think about. That's not, if you've heard the term heat death of the universe, that's not heat death of the universe. That's a different thing. Turns out we're really good at predicting ways that the universe might end. There's about 3 or 4 different options, depending on what assumptions you make. All right. How do we do some practice with this? How do we actually calculate some of this energy? It's always going to come back to E equals mc squared. If we're trying to do anything related to energy of nuclear reactions, it's always going to be E equals mc squared, or more accurately for us, delta E, the energy given off by the reaction, is equal to the change in mass times the speed of light squared. Do you have a question? Okay. So all we need to know is we need to know the mass of what we start with and what we end with a high degree of precision. So basically we need lots of sig figs. But then all we're going to do is plug in our change in mass into this equation to get our change in energy. So this is that reaction I was talking about, uranium-235. If you hit it with a neutron, basically if you fire a neutron into it and it lodges into this nucleus, it basically causes the nucleus to break apart in a predictable way that gives off lots and lots of energy and more neutrons. So this is the reaction that leads to an atomic bomb. Because what happens if you have a big enough chunk of uranium-235 and you hit it with a neutron, it breaks apart and gives off 3 more neutrons. If each of those neutrons stays stuck in that same clump of uranium, it happens 3 more times. And each of those causes it to happen 3 more times. You basically wind up with the reaction with what's called autocatalytic, which is a chemistry way of saying it's like a runaway train. It's just going to keep picking up speed. The reaction is going to go faster and faster and faster. And that's what they used to make the first atomic bombs. Was basically get a big chunk of uranium and just let it go through this process. The trick was just how do you figure out how to do that in a controlled way so it doesn't happen, in the refinery while you're making it. Turns out that was really it was more of an engineering problem, the Manhattan Project, than it was an actual science problem. They were doing some science along the way, but it was more of a logistics issue than anything else. All right, let's get a number for this energy. We've got 236 AMU and 235 AMU. With a lot of digits there. So what's our delta M going to be? Delta always means what number goes first in the subtraction. Final minus initial, right? So 235.86769. 67. Minus 236.05258. We're going to get negative 0.215. Did I do that right? Don't make me borrow in my head. I can't do it. It's something like that, right? We're going to be limited by our sig figs of C anyway at the end, so we'll call that good enough. What units do we need to put it in? It's physics units, right? Which is not grams. We want it in kilograms. So you can either use that conversion on your conversion sheet that converts AMU to kilograms directly. It's going to be something like 10 to the 26 AMU is 1 kilogram or something like that. I just always go to grams per mole. I do everything in terms of per mole anyway. Because then we can just say 1,000 grams is 1 kilogram, and now we're in kilograms per mole. If you do it in AMU and convert to kilograms that way, you're talking about the amount of energy for a single uranium-235 atom. We're never dealing with a single uranium-235 atom. We're always thinking about it in terms of moles. So we might as well do it in kilograms per mole. So plug in our negative point. Now it's 0.000215 kilograms per mole. Or even better, put it in scientific notation. We're not doing a conversion. It's times the speed of light squared. Speed of light, 2.998. 10 to the 8 meters per second. That whole thing squared. And if we do everything in physics units, if we're in kilograms here and we're in meters per second here, when we square that, we get meters squared over seconds squared times kilograms, which is the definition of a joule, is a kilogram times a meter squared per second squared. So as long as you put your units in right here, you know that your units are going to come out as joules at the end. We square that, we're going to get 9 times 10 to the 16 times 10 to the minus 4. We like 1.9 times 10 to the 13. Ten to the 16, 10 to the minus 4, it's 10 to the 12. Yeah, 10 to the 13. You should check me. I'm just estimating because I know that's really going to be really close. When I square this, it's going to be really close to 9 times 10 to the 16. 9 times 2 is about 1.8, except that's a little more than 2, so I called it 1.9. Might still be closer to 1.8, though. It is times 10 to the 13, though? 14. Ouch. That'll teach me. So these problems aren't too tricky as long as I give you this table, right? As long as I give you the table of products and reactants and their masses and with lots of sig figs, you add them up, products minus reactants, plug them in for delta M. And then it's just speed of light squared. That's still a really big number. All right. So if we, do you want to do another practice of those, or should we move on to some more interesting math?
Or interest.
More interesting.
Oh, yeah.
We'll come back to this one if we have time. All right, let's talk about radioactive decay in terms of time. We haven't done anything with time really in this class, right? This is not like a physics class where you're doing things like measuring how long it takes something to fall. No. Well, it turns out when you take general chemistry, or basically once you've had enough math, we start getting more interested in how time works with regard to these things. At this point, we haven't really talked about that because if you want to talk about how things change with respect to time, you need calculus. So basically, I'm going to hand wave through some calculus here and talk about some calculus concepts. I'm not going to ask you to do any calculus, don't worry. And it's going to end with, here's how we can actually calculate how long a radioactive sample has been around. We're going to end with, this is how radiocarbon dating works. Right, so if we want to talk about reaction rates, we need to define what a rate is. And so our rate is, we always kind of write it in a similar way. It's basically how much is a concentration changing over how much is the time changing. If I switched these variables out, if I switched the top variable for a y and the bottom variable for an x, what does that look like? Yeah, it's a slope. All this is, all the rate of a reaction is the slope of the line if you plot concentration versus time. Turns out that's all calculus really is how do you find the slope, or how do you find the area underneath a function? It is. You're just thinking about it too hard. If it seems more complicated. Right. So if this is the way we're going to define this, we can basically do it in terms of any of these concentrations, but we basically just pick something convenient, something we can measure the concentration changing. And here, this is what I was getting at with the change in concentration over change in time is just the slope of this line at any given point. The problem is, if we actually do this, we measure the concentration versus time of the product, you get this red line that doesn't have a constant slope. If this was a straight line, it'd be really easy to figure out the rate of the reaction because you just do rise over run. If it's changing constantly, though, something more complicated is going on in terms of the math. Something else is happening that's causing the slope to change as time passes. Why might the rate change? What's happening for a reaction to happen? Let's say that the reaction is, what's a good example? Let's say a reaction is two cars getting into a fender bender. Somebody gets rear-ended. What's going to affect how often that happens? If you had to guess, in South Lake Tahoe, are there more fender benders on the weekends or weekdays? Why? What do the tourists do? They don't know how to drive in the snow. It's true. I was just going with there's more cars on the road. Even if you assume the tourists are just as good at driving in the snow as we are, we know that's not true. But let's assume the fact that there are more cars on the road means that there's going to be more accidents, right? Well, a chemical reaction happens when two molecules bounce into each other with the right orientation and the right speed. The more molecules you have, the faster a reaction happens. Or the more times a reaction happens, which we measure as happening faster. So what's happening in this graph that's causing the slope to decrease? Loss of molecules. As the reaction happens, you've got less reactant left. So in our fender bender analogy, let's imagine every time a car gets into a fender bender, they get towed someplace and they're off the road permanently. If we said, okay, we're closing the passes, no cars in or out, but every time cars got into an accident, they get towed off to the junkyard forever. What's going to happen to the number of cars over time? It's going to decrease, right? We're going to run out of cars because every time there's an accident, the car's gone. Every time a hydrogen atom or a hydrogen molecule runs into an iodide molecule, they disappear. They turn into HI, but now you have less reactants left. Right, so this is what tells us we have to get more complicated with the math a little bit. We can't just do rise over run because the rate changes. This is what's called a differential equation. Basically, when your function is dependent on one of the variables that's in the function itself, that's self-referencing, it's called a differential equation because you change, it's continuously changing. So if time is affecting the slope, there's got to be some mathematical way to describe this. And it turns out there is. If we say that our rate is our change in reactant over change in time, we wind up, it's what's called a first order reaction, we get something that looks like this, a constant times that concentration. Turns out reactions can get more complicated, but this is the most common version, and this is the version that applies to nuclear reactions. So we're going to stick with this for now. Basically, if we do some algebra and a little bit of calculus, we get something that looks like this. 1 over concentration times change in concentration equals a constant times change in T. In calculus, this lowercase d is the shorthand for delta. It's basically delta, like final minus initial, if your final and your initial are really close together. If your gap gets really, really small between them. Actually, I think we'll flip the negative over here. So we're not going to do anything with this other than know that this comes from that same definition of a rate. And know that if we can then take this, those of you who are in calculus, have you seen anything like this before? What do you do with it? This is the simplest version of a differential equation that you can get. When you get it set up like this, you take the integral of both sides.
Erase it.
Luckily, these are really easy integrals to take once you know what an integral is, which again, beyond this, don't need to do U sub because the integral of 1 over a is natural log of a.
Who is we?
And then the integral of a constant is just the constant times that variable. So when we do this, we get something that looks like natural log of a plus a constant, don't forget your constant, equals minus kt. Don't forget your plus c. You'll fail the AP test. You'll probably not fail, but you're not going to get a 5.
Let's think anyone go.
So if you actually solve for what C is, you get C is the natural log of your initial concentration, which we can then combine this all together, and we get this. This is going to be the equation you actually do use. Not the calculus one, this bottom one. It still looks a little intimidating because it's got a log term in it. I get that. But it's just the button on your calculator. So if we can figure out what K is, this means we can figure out how much of our sample is left after a given amount of time. Or if we know how much of our sample is left, we can figure out how much time has passed. So this is the math behind isotope dating. Right? So radioactive isotope dating basically says when this sample was formed, we know how much of a radioactive isotope was in it. And now we look at this sample and it's got less. If we know what K is, we can figure out what time was. One example, the other versions of these integrated rate laws, it depends on what your initial reaction is and how it all works. When you take Gen Chem, you spend more time on this and look at these three cases. This is not exhaustive. There's other versions, especially when you get enzymes involved. This is the version we care about, though. This middle version is that's just a rearrangement of the way I have it written up here. So if you want to know why you have to study math before you can study science, it's because you need to know how the calculus works so that you know that you can trust this. And because turns out being able to understand calculus is really, really helpful in a lot of different aspects of science. Anytime time is involved, you're going to need calculus. All right, so how do we use this? Very carefully. No, it's not too bad. This is just another version of the same product or the same reaction. Equation. That's the term I'm talking about. What is T1/2?
Yeah, right now.
Any guesses what that means?
Half-life.
Half-life. So, half-life is the amount of time it takes to get to half of what you started with. It turns out for first order reactions, which all radioactive reactions are first order reactions, they're going to have a constant half-life, which means it takes the same amount of time to cut it in half every time. So if you started with 100 grams of uranium, we use uranium-238. Uranium-238 has a half-life of 4.5 billion years. After 4.5 billion years, you get 50 grams. Half of it has turned into thorium and then gone down that decay series, but half of it's still left. After another 4.5 billion years, that 50 grams will turn into 25 grams. After another 4.5 billion years, that 25 grams will turn into 12.5, and so on, infinitely. So basically, if you look at the amount of uranium-238 versus time, it's going to asymptotically approach zero. What does that function look like? You started with 100 grams here, and it's going to gradually get closer and closer to zero. So there's half. That's 4.5 billion years. There's another half. There's 9 billion years. What does this function look like? What type of function is it? Exponential decay, decrease. So the opposite of exponential growth. Basically, because of that negative sign there, we're talking about something decreasing. If we were talking about something increasing, this would be a positive number. And then you'd get exponential growth instead of exponential decay. So the fact that these isotopes all have a constant half-life means that if we know what their half-life is, we can figure out what K is.
Are there any elements for non-constant half-life?
No. Good. Well, we can create systems that don't have a constant half-life. Basically, by turning a first order process into a different process that's second order, meaning you have a concentration of two things that have to run into each other. all of the naturally occurring half-lives, all the naturally occurring radioactive processes are all just based on probability. There's a certain probability that a nucleus splits at any given minute. If you change that by saying, I'm going to slam a neutron into the nucleus, now it's not a first order process anymore. And then it doesn't have a constant half-life. For as far as naturally occurring stuff, though, we're going to say that all of them do. That's basically what we do to make a bomb out of it, is we hit it with other stuff. All right. If we know what the half-life is, what do we know about this ratio at the half-life? What is the definition of the half-life? Time it takes to decay to what? Half of what you started with, right? So in other words, when that's the half-life, A is half of A naught. Right? A naught is the initial amount. And so at the half-life, you know, whatever this number, it doesn't even matter what this number on the top is or the number at the bottom is. It just matters that it's the same. And the number at the top is half of what you started with. What happens to this ratio? It's just 1/2. It doesn't matter what you started with because they cancel out. So this is why it's a constant number. If it's a first order process and we have this ratio, at the half-life, these numbers cancel out and you just get natural log of 0.5. Which is just a number that you can get out of your calculator. 6.619? 693. So now, as long as we know what our half-life is, we can get K really easily, right? So that's where I was going when I said that these are the same equation written differently. At the half-life, this just turns into 0.5. And if you plug in number for the half-life, we can solve for K. Or if we know K, we can solve for the half-life. For whatever reason, radioactive particles get described in terms of their half-life instead of their weight constant, probably because it's easier to explain what a half-life is than it is to explain what K is to the average person. It's easier to think about a number in terms of time instead of K, which has units of inverse time. Inverse time is weird to think about. What is 1/seconds?
Seconds.
Turns out that's a real unit. 1/seconds is a unit you have heard of in computer science of all places, or in buying your new phone on Amazon, whatever. Not RAM. It has to do with how fast the processor works. It's in hertz. Hertz is 1/seconds, and basically means how many times does something happen per second. So when you say that your processor in your phone has 1 point whatever gigahertz, that means that it can do 1 point whatever billion calculations per second. But again, that's a lot harder to explain to the average person. So radioactive isotopes get talked about in terms of half-life instead, because regular time is easier to think about than frequency is. What do we get for the rate constant? What do we get for K? If we plug in this half-life for carbon-14. So half-life for carbon-14, 5.73, 10 to the 3 years. Basically, it's 5,700, and I think it's actually 25, but I don't remember those sig figs that well, so let's ignore that Just take it to 3 sig figs. 5.753 times 10 to the 3 years is how long it takes for half of your carbon-14 to disappear. So what's K? K is equal to 0.693 over negative 5.73 times 10 to the 3 years. Gets something like 1.2 times 10 to the minus 4.
Mm.
1.21. Except that that's not years. Sorry, I said years here. It's actually years to the minus 1. It's 1 over years. Which again is a weird unit. It's a frequency unit. It has to do with how often the decay events will happen. It's basically saying that if you have 1 mole of carbon-14 in a year, in 1 year, 0.00012% of it will disappear. Once we know K, we can do anything. As long as the anything you want to do is figure out how much time there is. You started with 0.110 grams of carbon-14. How much would be left after 11,000 years? That'd be too easy. What would be the time if it was actually going to be half of what you started with? 5,730 years to be the half-life. So we know it's not the half-life. So it's less than half of what we started with. It's pretty close to 2 half-lives, though. So we would expect it to be somewhere in the quarter of what we started with range. But to actually calculate it, we're just going to take this K value, plug it back in to the original equation. K is 1.21, 10 to the minus 4, years to the minus 1, times time, which is 1.12. I should have made these numbers a little more different. Times 10 to the positive 4 years. Gonna get something like 1.3. These are going to cancel out, right? We multiply it. So we're just going to get 1.2 times 1.1, which is going to be something like 1.3. That's not the hard part of this to solve, right? None of it's going to be hard, it turns out, but that's kind of intimidating. We're not used to dealing with logs much in this class yet. What does this ratio come out to be? Or this product, I should say. $1.36. What are our units now?
So 1.
We had 1 over years times years. No units. We got a unitless number. It's always concerning, so you should double check yourself when you see that. But we're being consistent with everything, and we're gonna take this and we're gonna raise it to an x as an exponent anyway. We don't really want units in the exponent. We don't know what to do with units in the exponent. For the most part, at this level, if you see units in an exponent, you're just gonna ignore them anyway. So as long as this unit and that unit match, then you're good enough. What you don't want to do is have one of these be in years and the other one be in minutes. If you have your rate constant in terms of 1 over years, you don't want to plug minutes in here because that won't cancel out. So you just need to make sure they're the same, because some of these rate constants are going to be in years or millions of years or seconds or minutes, anything in there. So as long as they're the same, you're talking about your time in the same units as your rate constant, you're fine. How do we cancel out natural log? We're trying to solve for A. E to the power of both. Yeah, E to the power of both sides. That's going to cancel out. Then we get A over 0.110 grams equals whatever that number is. Something pretty close to 0.25. E is usually get E by hitting second and then the natural log button. .257. Does it have any units yet? No, it had no units, and then we raised it, put it in an exponent. When you raise something in the exponent, it still doesn't have any units yet. So our units are going to be determined by whatever's on the bottom of this ratio. And it's pretty close to a quarter what we started with, right? A little bit more than a quarter. So the amount of carbon we have left is going to be 0.257 times 0.110 grams. .283 grams. Not very interesting when I write a dry question like this, because why do you care anything about carbon-14? Why is any of this useful? What do you do with carbon-14?
Make it wrong.
No, not this time. Usually, yes. We care about carbon-14 because carbon-14 is actually generated naturally in the upper atmosphere as a result of radiation from the sun hitting nitrogens in the upper atmosphere. It turns it into carbon-14. So there's a almost constant amount of carbon-14 in our atmosphere at any given point. The carbon that's in our atmosphere, what molecule is it usually present as? When people talk about carbon in the atmosphere, what are they talking about? Mostly CO2, right? Which, okay, so there's a constant ratio, relatively constant ratio of carbon-14 in all of the naturally occurring CO2 in the air. What uses CO2? What living organism uses CO2? Plants. What do they do with it? They turn it around. They photosynthesize. They make sugar with it. And then what happens to that sugar? It gets used by energy. They use it as energy, or we eat the plants and we use it as energy. Basically, all living things on Earth have a relatively constant amount of carbon-14 in them, because all living things on Earth eat plant-based sugars. You don't. That's impressive. Well, what are they eating? What are the carnivores eating? if you could maintain your carnivorous diet such that you didn't eat anything that had eaten a plant in the last 10 generations, you might be able to affect this a little bit. However, that's not really realistic. That'd be an interesting thing to see reported on nutritional facts. Like, it's not just organic, it's super carnivorous.
Imagine you totally.
So what this means is basically we can tell how long it's been since something stopped taking CO2 out of the atmosphere. We have, as long as we're living, we're taking in a relatively constant ratio of carbon-14. This is how we do carbon dating. We know that the carbon in living organisms is pretty constant ratio because the CO2 in the atmosphere, carbon-14 in the atmosphere is relatively constant, and everything eats those plants that eat the carbon-14. So basically, we can tell how long it's been since something stopped taking carbon-14 out of the atmosphere. What happens when something stops taking carbon-14 out of the atmosphere? Close. Basically, plants, it means the plant is dead. It stopped photosynthesizing. And if you stopped taking in plant sugars, then you stopped eating, aka you died. So basically, we can date how long it's been since something died by looking at the ratio of carbon 14 in its blood or in its tissue. So this is exactly how carbon-14 dating works. We can't carbon-14 date everything. We can only date carbon-14 date things that eat or are turned into, like we can do textiles, because what are textiles made of? Cloth, historically. What's the oldest type of textile that you can think of? Like, what do you make cloth out of? Linen, yarn, cotton. All of these things are from living organisms, right? So basically, like textiles, a lot of different types of paints. If your paint had some component in it that had living organisms in it, skulls, tissue, things like that. We can't date things like clay or pottery using carbon-14 dating because they're not made up of things that were living. But we can use different isotopes to date those. We have different ways of dating pottery, but luckily, eating and living things are relatively constant through the history of living things. So as long as we can date tissue, we can date what's found with the tissue. But only to a certain point. Does anybody know what the high end of what we can use carbon-14 dating for? Like the number of years? In theory, it's just going to keep getting cut in half every 5,700 years, right? So if we had sensitive enough detectors, we could keep going out forever and ever and just use carbon-14 dating. Realistically, though, we start getting limited by our instruments, and we can only really date things until about 50,000 years ago using carbon-14 dating. Anything older than that, we have to find another way of dating it, which luckily, once you get past 50,000 years, you start to get into geological dating. So you start looking at what rocks are found with that sample to try to figure out how old it is. If you look at all of that research that they do on like the earliest hominids, like Lucy, they're talking about, I want to say like 250,000 years to 500,000 years. And those are mostly fossilized remains at this point. So they date the minerals that make up the fossils instead of using carbon dating because there's no carbon left in those samples at that point anyway. So, all right. This is the last math that you need. If you can do this problem, that's the last math that I'm going to teach you. Good job, everybody. So next Thursday, I'll come and we'll do practice with this. We have some labs where you can practice doing some of this, practice some data plotting for next week. Probably just finishing up the assignment from earlier this week, or maybe I'll give you some practice problems.
That's yours.
So if it's 232, then that's going to be minus 4, so it should be 2.
There was the other new block routine. It like, well, I've seen it. Yeah, two and
Like Birdie. Oh, see, he has a slot. It's not. Sure.